for the invitation for this for our meeting and the possibility to give a presentation for you. As Professor Litak said, I'm dealing especially with magnetostrictive materials and magnetostriction. So yeah, as you can see, the subject of my presentation is magnetostrictive composite as a useful power source for energy harvesting applications. So let's start with a short outline of my presentation. For those of you which are not familiar with me, because I have seen that there are some people which already know me, but for those of you which are not familiar with me, I will briefly describe you my department, what we are dealing with, and later on I will tell you something about the project which I have right now and the result of this project. The partial result of this project I will show you today. So I hope that it will be interesting for all of you guys. And at the end, I will give you some additional information. So first of all, as Professor Litak said, I represent Wroclaw University of Science and Technology. So there was some change in our name. So the science part was added about 2 years ago. So there might be some difference if we are looking for our university. So in our department there are about 53 employees, including PhD students, and also including scientific and technical staff. So you can clearly see that most of us are men, but there are also a part of women, so it's not very muscular department. So we already did, and we already have we have many projects in different areas of interest. If you look closely to just a few of those which I just mentioned here during these presentations, we are dealing with hydrogens, we are dealing with metallic glasses, but also with, as I said, smart magnetic materials and nanotechnology. So there are a lot of things which we are doing in our department. Yeah. So according to the project and to those projects, we have many different partners, both scientific and industrials. As you can see here, I just gave you information about some of them because there's a lot more of those smaller or bigger partners, but there will be not enough time to tell you about this during the presentation. So yeah, so our department is actually divided to 9 research divisions. As you can see here, I represent the Smart Materials division. So this is the group of about 5 people which are dealing with this type of materials, and we are especially dealing with magnetic smart materials, which is important because I know that most of you are more or less dealing with piezoelectric materials. You're more focused on electro material than the magnetic ones. And I myself, I am focused especially on magnetostrictive materials. So the one that are best known is terphenyl D-alloy, of course. So this material has a magnetostriction effect, but it also has opposite magnetostriction effect, so-called Larry effect. And my whole scientific history is connected with magnetostrictive materials. I started with bulk magnetostrictive materials, so the pure terphenyl D, but in master and PhD thesis, I focus on composite materials. So I was dealing with epoxy matrices, but also with polyurethane. Retanic matrices, and based on the result of my scientific work, I obtained a result that the composite material might be useful as or might be as good as the bulk material, even though that the magnetostriction effect is a little bit lower than for the bulk material. It's about 2-3 times lower, but it's still much higher than for typical magnetostrictive materials such as iron, nickel, or cobalt. But during my work, I also start to dealing or interesting in the reverse magnetostriction effect, so Villari effect, because we have found that it might be useful also for energy harvesting applications. We were already aware that many scientific places, many universities are dealing with piezoelectric materials in this area, so in area of energy harvesting. And we thought that maybe we'll go in other ways, so this is why we decided to deal with magnetostrictive materials as a source or as useful material for energy harvesting. So it was the beginning of my connection with energy harvesting subject. So here are some results of our activities in this field, but I will tell about it a little bit later. But first thing first. First of all, I just want to describe the project that I already right now doing. So the title is, as you can see, composite magnetostrictive nanocrystalline materials for use in the field of energy harvesting and transformation. So the fund is not very high. It's about €250,000, and it's supposed to take 3 years. So right now we are actually in the middle of the project. So this is why I just want to show you some result, where we are and how we get to this point. So I will start from the origin of the project. So how we begin, how everything begin, and it's connected with our other department. So Department of High Pressure Vessels and Structural Health Monitoring Laboratory. We were talking with our colleagues from this department, and they mentioned us that it will be useful or great to have other power source than the wires, because usually when they have some objects to monitor, they are adding some sensors, and of course you need to power up these sensors, and usually they were using wires, and all of those wires were attached to the PC, and then there was a lot of wires, a lot of sensors, and a lot of calibrations. And they asked us if it will be possible, or we were talking that it will be useful to have no wires for those sensors. So the first thing is, which we are thinking about, are batteries. So why don't we use the batteries? So we agree that batteries will be useful. So instead of using wires, let's just power up these sensors and the devices with those sensors with some batteries. But some additional problems occurs during our next meetings and so on. So we start thinking about batteries, but we also take into account cons and drawbacks and positive things. So here are the things that we were thinking about. So batteries, capacitor or capacitors, they are the useful power source. I know that every one of you know it, but we made some researches. So in order to maintain the system powered with batteries, we must still remember that there will be some problems with different objects. And this is why I'm talking about the high pressure vessels department, because they were a problem with their vessels, because they wanted to monitor these vessels inside of the structure, so not outside of the structure but inside. So it will be very hard to, for example, change batteries in such a vessel, because okay, you can apply during the production of the vessel this type of sensor and the monitoring device and so on, but there will be a problem with the power source still, because it will be impossible to replace the battery. So yeah, when the battery is getting lower and lower, then after a few years there will be a problem with powering this type of sensor. So we've made some researches and gather information about batteries and other sources of energy. So we can clearly see that most common right now batteries are lithium-ion batteries. So they have a pretty high energy density in comparison with lead-acid batteries or supercapacitors. But there is a problem with time span of these batteries and the lifetime of the batteries, because each batteries have fixed lifespan and they fade gradually. And the very important influence on the battery lifespan is the environmental conditions. And usually producers tells us that we supposed to be working with these batteries in a specific range. So it shouldn't be powered till 100%, and we shouldn't drop with the voltage or the density under the 25% of the batteries in order to have the batteries longer lifespan. So we can clearly see from this chart here that the best or the longest lifespan we receive when we are in boundaries between 75-25% or even less. So when the boundaries of the usage of batteries is even less. So this is also the drawback of batteries. So now, based on those informations and our experience in the field of magnetostriction and the Villari effect, we start thinking about energy harvesting. So now here are the answers why we decided to start dealing with energy harvesting itself. So as I said, my previous scientific and research work was the basic reason. Then, of course, we know that more and more electronic is miniaturized and those devices are low power, so we don't need to give a lot of power to those devices in order to make it work. And also ecological reasons. So why don't we replace the batteries, which after the life, after their life, we need to throw away and we need to recycle, and it's very it's not very ecological. And also we need to remember about the regulations that in many countries, not in the whole world, but in many countries, regulations are force us to use as many so-called green source of energy as possible in order to make our planet better in health. So those are the reasons why we start to deal with energy harvesting project. So my project goals are given here. So we have two main goals. The first goal is to create new composite material that will enhance the Villari effect. And in order to do this, I would like to combine magnetostrictive material, even already known magnetostrictive material in the form of powder, for example, like terphenyl D, with new nanocrystalline material with specific magnetic properties. Based on the literature, we can say that there were already some trials. Oops, what has happened?
Try to share again. Oh yes.
Sorry, yeah, something happened.
Okay.
Just I will need to skip to the right slide. Yeah, okay. There it is. Sorry, my mistake. So there were some different trials with this kind of composite, but till now I haven't seen magnetostrictive composite material with addition of magnetic metallic add-ons. So usually there will composite just based on the powder or lamels or something like that, or rods of terphenyl D, but there were no additional phase, which in our mind might help to improve the Villari effect, or at least will give us possibility to lower the price of the final material. So this is our main goal, to create or produce new composite material. And additionally, we would like to develop a prototype device based on this material. So we already did some trials with devices that we already prepared. So one of here is an example of such material, so such a device. So you can clearly see that we have the simple electromagnetic device, where we have just coils with powder of terphenyl D with additional magnetic field bias, magnetic field. So someone may say that this magnetic field will give us everything that we need. However, we done some experiment with the device that we have here, and it occurs that only terphenyl D, so the magnetostrictive material, give us enough amount of energy to power up some devices. This device were connected with LED, three LEDs, and we were able to power up all those, all three LEDs. So it was the easiest configuration of the magnets, coils, and terphenyl D powder. And after that, we started to make some additional changes in our device. So we add some bulk material. So you can see here the red rods are definitely the bulk material. Additional magnets we have here with the blue color, and these devices gave us additional power source, even to power up microcontroller. So we were checking different types of cores, as you can see on the left side, so solid terphenyl, composite terphenyl, this, and also cores made of terphenyl D powder. Of course, the best result we obtained for the terphenyl D itself, but there were also promising results for the composite structures. So here are the results for the bulk terphenyl D or the microcontroller that were power up. So those black lines that we have here, those are the signal from the microcontroller. So you can see that we obtained many signals from the microcontroller during the 2.5 milliseconds. So it's pretty enough time to receive information from the to power up microcontroller, to send data from the microcontroller to, for example, some sensors, and to obtain data from the sensor, and to store the data, for example, in the flash memory or somewhere. So this is one thing. But as I said, this project is mainly focused on composite based on magnetostrictive material and nanocrystalline material. And in order to do this, we needed to develop some new materials, and we based in our development in such materials. So they are mostly based on iron, silicon, and boron. However, we also some of you may know those that there is part of material, or this materials might be known as med class or fine meds, but we were trying to change the composition of the alloys. So this is why here we are only given the element information, not the amount of each element, because the creation of new material is very complicated, and we decided to base on a non-crystalline material. So to ensure that the obtained material will be with nanocrystalline structure, we needed to find a way how to obtain the nanocrystalline structure for sure. And I know that you're supposed to know that when you are dealing with materials, so you are melting it and then you are cooling this, you don't sometimes, or usually, you don't know what type of structure you can obtain. So usually it will be crystalline structure, but it will be not a nanocrystalline. The crystallites will be bigger, so microcrystalline, and it's not enough for us. So we needed to be sure that obtained structure will be nanocrystalline. So in order to do this, we also started with additional area of our department, so metallic glasses department. And with this department, we were able to start producing metallic alloys. And we used two methods, so arc melting and melt spinning. So here we have the device for arc melting. And with arc melting, we were obtaining we're just melting the elements itself together, and after that, here we have a chamber where we can also use section casting, as you can see here. And with this method, we are able to obtain rods with diameter of 3 and 5 millimeters. But what this method gives us? The method gives us a very high speed of cooling of the device, of the material. So in this way, we are able to obtain metallic alloys, but in a form of metallic glasses. So I'm sure that you know that the glasses has amorphous structure, so there are no crystalline material or structures. So this is the way how we are able to obtain also metallic glasses. So our material supposed to have amorphous structure, and from the amorphous structure, we are able to change the structure to a nanocrystalline with specific heat treatment. So this is the section casting device, but we have also the melt spinning device where we are melting alloy, as you can see here. Then we have a copper wheel, which is spinning with very high angular velocity, and it's about 40 kilohertz of angular velocity. And after melting, we are just curing the melted alloy on the wheel, and in this way we are obtaining also amorphous ribbons. So when we obtain the material, then we would like to create composite material with magnetostrictive material and maybe with additional matrices or not. We will see in a couple of months, I think. So this is the basic of our idea. So from the rod, we can cut pieces, as you can see here, and then join these pieces with composite material in a shape of, let's say, also rod with terphenol or magnetostrictive material, and also, for example, epoxy resin. But we are thinking also about other type of composite. So instead of taking bulk material, so in a form of rods, we would like to crush it to the powder as we had with magnetostrictive powder. So we would like to mix everything together and then get the stack of such tablets, and then we can add everything together and obtain also magnetostrictive composite with nanocrystalline particles. But how we would like to do this? So we would like to use LTHP method, so low temperature, high pressure method, with a usage of high pressure press up to 8 gigapascal. We already made some preliminary test with terphenol D material and the powder of terphenol D. So here are the results. So as you can see, we obtain tablets of terphenol D powder, and then we stick everything together and obtain such a, let's say, a rod. But as you can see here, it was very narrow and not very centralized and so on. So we decided to make it better for experiments, and we tried to machining. And it occurs that the method of low LTHP allows us to obtain material which is hard enough or good enough to even machine it. So it doesn't broke during the machining, and we obtain a pretty nice rod. So you can see here places where each tablet is attached to each other. So right now we are trying, we would like to use this method also for connecting or adding a magnetostrictive powder with nanocrystalline material. So this is why I show you two ideas how we would like to create our composite. However, I still don't know if it will be possible to do this in both of those methods. So if the high pressure method wouldn't work, we can also we always will be always able to use some other matrices, for example, ceramic one or epoxy or other matrices, and then also obtain composite material. But let's get back to our material. So material under development. So here are the results of the SEM images for the obtained material. So here you have only some examples of the material that we already prepared. So you can see where we were taking these images from those materials. So left edge in the center and the right edge. The left edge and the right edge are very similar, so this is why I just show you the left edge and the central area of each sample. So you can clearly see that those two alloys are very different. If we are talking about the structure of each of those materials, so in this 5-element alloy, we can clearly see the crystalline crystallites, and they are small in the at the edge, and they are even bigger in the central area. So it's Obviously, it's very related to the process, how we are in process of production. So the gradient of temperature is going from the outside to the inside. So it's the highest temperature we have in the inside. So this is why the crystallites are able to grow. So, but if we compare the top images with the bottom images, we can see that in the bottom images, the structure is barely seen. So it tells us that it might be amorphous amorphous material. And we can see that in the central area, there are some differences between the colors. So there might be also different phases of material. So after that, after the SEM researches with additional nano indentation researches. So we have the same two materials, and here are the images from the nano indentation device. So in nano indentation device, we are working with polarized light. So we can see that previously 5-element material is still crystalline, but we can see also very clearly that our 4 elements material from the previous slide, so the one from the bottom, seems to be also crystalline, however with some dendrites. So, but these dendrites are, let's say, soaked in metallic matrices. So with this method, we were able to obtain instrumental elastic modulus for those two materials. And after that, we also check the elastic modulus for other materials with 3 different methods. So you can see that we were using the mechanical method, so 3-point bending, acoustic, let's say, or vibration methods, so transfer vibrations, and as I previously mentioned, instrumental modulus of elasticity. So we can see that instrumental modulus of elasticity and 3-point bending are very similar to each other, and transfer vibrations are not quite as the elastic modulus is not as big as it was in previous methods. However, we may say that they are very similar to each other. So till now, we are able to deal with about 20 samples. So I just gave you information about a few of those and show you where we get. Right now, we are taking investigation over the magnetic properties of these materials. So we are dealing with vibrating sample magneto measurements, but we had already some results, but unfortunately, I didn't have time to analyze those. This is why I don't want to show you today this. But I hope that maybe in a few months I will have opportunity to share with my additional result, and I will show you how far we get with the new materials, and maybe we'll be able to already show you the result from the devices based on the composite, but we will see. But what else is going within the project? So we also in parallel time we are dealing also with the devices and electronic system which might be powered up with created material. So we prepare the device, we call it as harvested node, with 14 degrees of freedom. We call it as 14 degrees of freedom because we are taking into account each parameters which might change. So for example, if we have 3D accelerometers, we have 3 degrees of freedom in this device. So 3D and 3D. So we have already 9 degrees of freedom till now. So we have also possible to measure the pressure. We have also microphones. We can measure temperature, humidity, and light intensity. So all of these together give us 14 degrees of freedom. So our first goal will be to try to power up this device and to obtain information for all of these sensors, or at least from some of those sensors. But the final goal for us will be to be able to power up devices inside of closed environment, as I said at the beginning of the presentation, for example, for the vessel. So this is why we have such drawing here. So we'd like to transfer the power, so power up the device, and then obtain the data from the device. So here is a simple sketch how we would like to do this. So we already did some trials, however, with solid terminology, and this is the example of those trials. So we have here actuator, harvester on the other side, and the harvester and the device are closed in the glass container, and it's the container is closed, so we don't have possibility to get in there. So those are the conditions that supposed to be in some place. So our trials, or we were able with such a system, we were able to power up the device inside and to receive information about the temperature, because this plate here has sensor temperature, and we wanted to receive the information about the temperature. And if we are talking about the transfer of energy, we are using both magnetostrictive and piezoelectric actuators and harvesters, and we were making some combinations of those, because in some cases the better pair is when we have magnetostrictive actuator and piezoelectric harvester. But in some cases it's better in opposite way. So we have harvester as a magnetostrictive device and actuator as a piezoelectric device. So this is one of the examples. So the other example is, as I mentioned, not only to transfer power, but also we wanted to transfer some data. So here we have such construction, let's say. So here we have rails. Between those rails we have harvesters and actuators, and we are trying to send information through the rail from actuator to harvester. So it's clearly see here in this video. So we can see that wave is going through the rail. We can find what was the frequency of our system, and we were trying to get to the point where we can obtain the highest voltage on our system. So for example, in this case it will be 24.3 kilohertz. So with this frequency we were able to send highest amount of energy, but also between the energy we were also able to send some information. So we also try to send the energy on the longer rail. So the previous rail has about 1 meter of length. This one that we have here has about 6 meters of length, and it was possible to send to send, let's say, power from the one end of the rail to the other one. And you can see here we were also able to check what is the best frequency of work of the system. Of course, you may say that usually systems are not working with the frequencies that we would like to have. Yes, that's true, but based on our system, we are able to check what is the best frequency, and we can try to tune our system in order to have this frequency of work, to have the highest values of energy, which we were able to harvest. As a summary, I can say that within the project, we'd like to try to develop new composite material based on magnetostrictive phenomena, which will be able, or which give us possibility to change mechanical energy to electrical energy and then power up the devices based on this material, based on this solution. We hope that our new material will have high efficiency, but we'll see. It's still just our assumptions. But let's see what the life brings us. So what else I can say? Yeah, I would like to mention two more things. So this is everything what I would like to tell you about the project, but I also would like to invite you for the conferences. So this is the first conference. It's supposed to held on 17 till 10 of September of this year, but as you know, due to the fact that we have COVID pandemic in the whole world, it was postponed. So organizers postponed this meeting to the 2021 or 2022. However, as you can see, the thematic sessions are connected with the thematic, with the subject that we are dealing with. So it might be interesting for you, this conference. So we'll see if this conference will be on next year, or maybe it will be in 2 years. And the second conference, it also supposed to be on September 2 to 4. And as you can clearly see here, the thematic sessions are mainly focused on fatigue. However, there's also a session which is connected with smart materials. You can see that we are talking about metallic smart materials. However, everyone is invited. So if you are dealing with ceramic materials or polymeric materials, you are also invited to this conference. I can tell you that I will be the head of this session, so you are more than welcome to join our conference. And right now, I know that this conference is supposed to be postponed to the second half of 2021, and as the organizer said, it also more likely will be on September. However, we will see, but the venue will be for sure in Wroclaw. So I encourage you to join our conferences, and maybe we'll meet there in near future. So I would like to thank you very much for the attention, and if you have any questions, I am for your